Hello everyone. Okay, in this video we are going to go to the new section called damp oscillation. Previously we introduced a simple harmonic oscillation, and now we are going to damp oscillation. Okay, and damp oscillation actually it's used a lot in engineering field. Okay, let's take a very simple example. It's like your car suspension. Yeah, your car suspension, because suppose you have a car, you're going to a bumpy surface. Okay, so the bumpy surface will cause the vibration of the car, right? But the vibration of a car, it will make you feel dizzy. Okay, if you if you ride a car and the car has very bad suspension, you'll be very feel very terrible and feel dizzy. Okay, and how to absorb this vibration energy from the bumpy surface. Okay, you often see your car, if you look under right under your car. Okay, your tire always connect to a suspension system. In your suspension system, you will see there's a spring. Okay, this spring will absorb the vibration energy from the bumpy surface. When your car across the bumpy surface, you absorb the vibration energy from the bumpy surface. But the problem of spring is, yes, spring can take the energy, it can store the energy, but at the same time, after it absorbs energy, and then it will release the energy. Just like the simple harmonic oscillation we demonstrate before. Okay, and here, yeah, the spring is doing a simple harmonic oscillation, right? Simple harmonic oscillation, it will take the energy, from here. It will absorb the energy. Okay, but after absorb energy, it will going back to release the energy, and then absorb energy again and release energy. Okay, so the spring can absorb the energy, but at the same time, it will also releasing the energy. Okay, but when the spring release the energy back, release the energy, uh, you okay, that's not what we want. Okay, because if the spring keep doing the absorption energy, releasing energy, absorption energy, and releasing energy, the your car still very bumpy. Okay, okay, that's not what we want. So we have to come up with another device connected with the springs. Okay, and this device we often call it damper. Okay, this damper also take this damper also can damp your system. It can damp oscillation. Okay, so that's why it's called damp oscillation. Okay, we want to make the oscillation disappear as soon as possible, or the system will just keep vibrating. Okay, it will be vibrating like crazy. So we need a damper, and there is a very simple demonstration of the damper in this video. Okay, you can look at this video. I think it's very demonstrate the device, the damper device very clearly. And the damper, yeah, often there's a damper, and in a damper we often input some viscous fluid. Okay, and this is a piston here, and immersed in the viscous fluid. And this very simple device. Okay, this very simple device, very simple damper, but this device can dampen your oscillation. And often the drag force or damp force is proportional to your velocity. Like what air resistance, or for example, air resistance, your plane or jet flying flying in the air, it will feel the resistance. The plane will feel the air resistance, and the air resistance. You can, for various considerable situation, drag force, air resistance, drag force for air resistance, you can proportional to the also proportional to the for the velocity. Or if you have object immersive fluid, if you have object in the fluid, okay, and the fluid pass through this object, and this object will feel some resistance, and this resistance, and or yeah, maybe that's maybe very right example. Okay, suppose you have object moving in the fluid. Okay, and the object moving in the fluid, again the object will also feel the resistance from the fluid, and the resistance force sometimes proportional to the moving velocity of your object. Okay, so most of time, so we will have a very simple model here. Okay, so we have a system, also a mass spring system. Okay, and also right now we have to add a device which provide the damping force. Okay, so right now your system you have elastic force and damp force. Okay, and then we'll use Newton's equation of motion. Yeah, same thing. Newton's equation of motion. As I mentioned, F net force equal to ma. And right now, net force, you have elastic force and damp force. Okay, and B, we call it damping parameter. Okay, B, we call it damping parameter. And dx dt is a velocity. Okay, so the drag force or damp force is proportional to your velocity. Okay, and the proportion number is B. Okay, it's called damping parameter. So this is our equation of motion. Okay, so right now we have to solve this equation of motion. Okay, and it's one more time. It's a second order ordinary differential equation. Yeah, but right now you don't have the capability to solve this differential equation. But eventually, in your second year engineering mathematics, you will all learn how to solve this second order ODE. After you learn how to solve second order ODE, you will realize that this is very easy to solve. Yeah, believe me, this is very simple second order ordinary differential equation. Very easy to solve. And once you learn engineering mathematics, this is very easy to solve. But right now we don't have the ability to solve this differential equation. But yes, just like what we did in the simple harmonic oscillator, we can guess the solution. Okay. So how we guess the solution? We can guess the solution like this. Okay, we can guess the solution like this. It's amplitude times the cosine function, which is oscillating function, and with time exponential decay function. Okay, with time exponential decay function, because because right now our system, if our system is very simple harmonic, is a simple harmonic oscillation motion, we only have elastic force, right? We only okay, let me do it. Okay, this is simple harmonic oscillation. Our system only has the elastic force, and the solution is a cosine. We guess our solution is a cosine function because it's keep doing oscillating. Okay, but right now our system, we add the damping force. We add a damping force in the oscillating system. So intuitively, yeah, we are right now we are originally an oscillating system. We will add the damping force in the oscillation system. So intuitively, so this system will become a damp oscillation system. So we and the cosine function is oscillating. Okay, so how could we make a damp oscillation? Okay, so we just guess the solution. We just guess the solution, right? We just guess the solution like this. Okay, so we still have the term in simple harmonic oscillation, amplitude times the cosine function, oscillating function, but we intentionally, because it's damp oscillation, so we intentionally this solution with times exponential decay function. Okay, this is exponential decay function. Exponential decay. Okay. Okay. Yes, you have oscillating function, oscillation function, but you times the exponential decay function. So this function times together will become a decayed oscillation function. So eventually, when t is very large, so this exponential decay will take effect and then erase all the oscillation in the system. So we can guess the solution like this. Okay, and the exponential function we guess exponential function is also function of time, but we add the parameter called beta. Okay, called beta with the exponential minus beta t. Okay, and the same in the simple harmonic oscillation, the amplitude and phase constant are also dependent on the initial condition. But so right now we are not going to solve the amplitude and phase constant in damp oscillation. what we are trying to find is what is our our angular frequency. Yeah, we are going to after these two terms. What's our angular frequency in damped oscillation, and what is the beta? Because we this is what our assumption there's a beta in front of time. We have to find the beta, and we have to find the angular frequency in the damped oscillation. So how can we find the angular frequency in the damped oscillation and its beta? Just put this assume this is our assumed solution, okay, our guess solution, okay. Put the guess solution back into the differential equation, okay, and put the guess solution okay, into the differential equation. Yeah, it's too long, so I call it DE. Put this the gas solution back into the differential equation, and then we can find the angular frequency for damped oscillation and find out what beta it is. Okay, and the calculation detail is kind of too very long. Okay, so I just write down, okay, in advance. Okay, so we want to put the x back into the equation, because what's the minimum solution? The minimum solution just means that if you put a solution back into the equation, it will valid. Okay, so let's put this x back into the differential equation. So if we put this back into differential equation, you have to do two things. One is do the first derivative of x, and also you have to do the derivative of x and second derivative of x. Okay, because this function is exponential function times the cosine function, so there's a two function in x. So when you do the derivative, yeah, it will take us a long time, because you have to use a chain rule in your calculus class. What is a chain rule? Suppose we have two functions f and g times together, and when we do the derivative, you will get the derivative of the first term times the second term plus, okay, no derivative on first term and times the derivative of second term. This is called it's not chain rule, it's called product rule. Sorry, it's called product rule. So we have exponential function and cosine function in there. So if you do the derivative of x respect to time, yeah, lots of work because of the product rule, right? But eventually you will get these two terms. But let's not finish, because we have to do the derivative of x, do the second derivative of x. So the second derivative of x, just put this derivative of this derivative of this derivative again, okay? So it has many terms pop out. So it's a very long time calculation, so just be patient. Okay, so I have already write the dx dt and dx squared dt squared. Okay, I have to finish it, and we have to add all this together. Okay, so what we're trying to do is, okay, let me write down. That's why I'm trying to write down. What we are trying to do is dt squared plus mb dx dt and plus, I think it's mk over m, x equal to 0. So we'll have the dx dt, and we'll have dx squared dt squared together, dx, the second derivative of x. Okay, just lump everything together and see what happened. Okay, so what will you see? Okay, so let me write down. Okay, so let me here I write down what is x. X is equal to what our guess solution, a times exponential minus beta t and cosine omega t plus phi. Okay, so we first of all we add the term with exponential minus beta t times cosine omega t plus phi first. Okay, here you see we have here one term, here is one term. Okay, don't forget here there's another term. So we add this term together first. So we have, what we have. Okay, so first term, first term is beta square a minus omega square a, and plus b over m, and here is because dx dt is here, so we have minus beta a. Yeah, we have minus beta a m plus k over m, so we have a here, and times x minus beta t and cosine omega t plus phi. Okay, this is the first term. And next then we group all the term with exponential minus beta t sine beta t omega t plus phi. We group the second term together. So what's the second term? What's our second term? We have okay, here is one. Yeah, here is another. Oh, sorry. Not his one. Here is another one. Yeah, here is exponential minus beta t sine. Exponential minus beta t sine. So, okay, let's put all this together. So we have beta omega a plus beta omega a. That means 2 beta. That means we have 2 beta omega a and plus b over m. What's our dx dt? Dx dt. So what is this? Minus omega a. Okay, minus omega a. And minus omega a and plus k over m. Yeah, this x we only have cosine, so there's no sine. So okay, so that's okay, plus 0. Okay, and add this all together, and this equation will all add them together. It will become 0. Will come to 0. Okay. Oh, sorry. It's equal to 0. Okay. So we have these two terms. To this, we put the solution. Okay, we'll put the gas solution. This gas solution back into the differential equation and get this relationship. Okay, actually a very complex term, but actually a very simple. This is just a number, some number times exponential minus beta t cosine omega t plus phi. Plus, yeah, there's a plus here. Yeah, there's a plus, a constant. Yeah, there's very complex term here, but eventually it's just a constant. A constant times exponential minus beta t times sine omega t plus phi together, and add these two terms together equal to 0, 0. There's only one solution. There's only one situation. Okay, we can validate this equation. This because beta square a minus omega a minus a plus mb minus beta a and plus k over m a equal to 0. And the other situation, this term must be 0. Okay, and the second term, omega a plus b over m minus omega a plus k over m. K over m. Sorry, this is wrong. No, this term here. Okay, so this term is 0. Is also 0. Okay, so from these two equations, okay, because every term has the a, so cancel out. Okay, so what do we, by these two equations, what do we have? First of all, okay, let us see. Okay, beta square minus omega square. That's the first term. 1 plus b over m, and this is beta, and this is minus. Okay, so let's put a minus here. Let's put a minus here, and plus k over m and equal to 0. And this one is, yeah, we can do a bit further reduction, so everything like omega. So we have 2 beta minus b over m is equal to 0. Okay, so did I get this right? Okay, so first of all, we get the beta. What is beta? Beta is equal to or 2m, b over 2m. That's beta. Okay, it's related to mass and damping parameter. Yeah, don't forget this is mass. Okay, b just the damping parameter. Okay, we find out the beta is it's a b parameter. Okay, it's damping parameter divided by mass and divided by 2. Okay, and what will we get for the first term? Okay, first term. Okay, first equation. Yeah, don't forget our goal. Our goal is trying to find the omega. Yeah, don't forget our goal. Okay, we're trying to find omega and trying to find the beta. Okay, right now we find the beta. And the second one is what is our omega. Okay, and omega looks like much more difficult to solve. And let me see, b over m 2n over b. Let me see. It looks like very difficult to solve. Oh, okay. Let me see. So in the damp oscillation, yeah, we let the omega 0. Yeah, in damp oscillation, we have two frequencies right now. One is natural frequency. Okay, natural frequency is equal to k over n. Natural frequency squared is equal to k over m. Okay, it's natural frequency because it related to your elastic constant mass. It's a parameter of the system, so it's called natural frequency. And omega right now is the one to be after. So so let's write down this term. Let's solve this term. Yeah, this term is more difficult. This equation much difficult to solve. So, but we already solved the we already solved the beta, so maybe it's not that difficult. Okay, so beta is b over 2m. So b over 2m square minus omega square minus beta is b over 2n. So mb and 2mb. Okay, so m plus omega 0 square equal to 0. So our omega square is omega 0 square. And plus, let's say we have to reduce this a little bit. 2m square. I think we have to make some way. So the first one is 4m square b square minus 2m square b square. So it actually is minus 4m. Okay, so it's minus 4. 2m squared, 2m squared. So minus 1 over 4 minus or m squared b squared. Okay, okay, we get the answer. The answer is correct. Okay, let's make it more make this answer more beautiful. 2m b squared. Right, correct. Okay, so our omega is omega 0 square minus 2mb square, right? Okay, I think this is the right answer. Let's go back to PowerPoint. Did I get the right answer? Yes, it's the right answer. Okay, we finally find omega. And you will find in a damped oscillation, your oscillation frequency is no longer the natural frequency. It's no longer k over n square root of k over m. Okay, you will find your oscillation frequency is smaller than the natural frequency. It's no longer k over m square root anymore. And your oscillation frequency kind of controlled by your damping parameter. Okay, this term relates to the damping parameters, right? So in damped oscillation, the angular frequency of damped oscillation is no longer to natural angular frequency anymore. Okay, it controlled by your damping parameter B, and it also the damp parameter. The damper output also control your beta, and it's very important. Okay, let's back to this slide. Okay, we finally get this solution. Okay, the solution will look like this, right? Yeah, this is just what we found. We found a beta. Beta is B over 2m. Okay, and this term is very important because you will see this is a picture of this damp oscillation, and the envelope. You see there is the notation here. The amplitude decrease as a times exponential blah 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 b over 2mt. Okay, so actually this b is very important. Your damping parameter control the decrease of envelope. The b will the parameter b will determine how fast how fast you can dampen the oscillation. Okay, if you have a large damping parameter, you will dampen oscillation very quickly. But on the contrary, you have very small damping parameter, the oscillation will keep move on, keep move. You don't wait for a very long time to damp. You need a very long time to damp oscillation. So damp parameter control how fast you damp, how fast you damp oscillation, and also it control the oscillation frequency in your system. Okay, angular frequency in your damp oscillation. But this term, I'm not sure. This term because I did some calculation before. This term is not that huge compared with natural frequency. But maybe that's my wrong impression. But it also tell you, this equation also tell you damping parameter control the angular frequency in the damp oscillation. Okay, so I just stop the video here, and because we can use this equation to classify many kinds of damp oscillation. Okay, so I think I will do introduce the different kinds of oscillation in the next video, and then we'll do the practice for the damp oscillation. Okay, this is example 13.6 is from textbook, and we'll do it in the next video. And there is some homework very similar to this. Okay, I think there's 3 to 4 problems similar to this. Because you are not that familiar with damp oscillation, so I make lots of homework for damp oscillation. Okay, I just start a video here, and see you in the next video. Bye bye.